We started this section on, what day is today? Today's Tuesday, right? We started this on Thursday, and we ran out of time. So I'm going to go through the first part of it kind of quick because we've gone over it. We were talking about trends that we can observe on the periodic table, and the first one was atomic size. And so what we talked about was that as you go across the period left to right, the size decreases. Now let's just go directly to this picture here. As we go across lithium, beryllium, boron, etc. to neon, the size of the atom decreases. This is counterintuitive. We're adding protons, we're adding electrons. It should be larger. But quantum mechanics explains why this is. We are adding electrons in the same principal energy level. They are roughly the same distance from the nucleus. So we would expect then that the size would be the same. But because we're adding protons as well, the charge on the nucleus increases. The increased charge pulls the electrons in tighter. So as we go across, atoms get smaller. Going down, it makes sense the atoms get larger. So we were in the middle of doing this example. We already did letter A. Let's do letter B. Choose the larger atom in each pair, rubidium or sodium. Well, you have to find them on the periodic table. So rubidium is right here, and sodium's right there. Which one's larger? Rubidium, because the trend is as we go down, they get larger. So rubidium is larger. What about tin or bismuth? Well, again, we're going to find them on the periodic table, right? Here's bismuth, and here's tin. The trends were going across, they get smaller. So using that, we would predict that bismuth is smaller. The other trend, though, is going down, gets bigger, and so that predicts that bismuth is larger. Opposing trends, what do? We throw up our hands and say, I quit. No. I won't ask you one of these on a test. This is tricky. Let's go back to this. If you were forced to choose, going across, this change is generally a little bit smaller than going down. So I'd go with the going down trend if I was forced to choose. So in that instance, I would pick bismuth if I was forced. But I would not ask you to do that because that's opposing trends. Fluorine or selenium? Well, let's get rid of these guys and find fluorine and selenium. Where's fluorine? And here's selenium. The trend is going across gets smaller, so that predicts selenium is larger. Going down gets larger, that also predicts selenium is larger. Okay, that's better. So any questions about those? These are general trends. There are exceptions, but just good to know the general trend. Okay, another one is ionization energy, and this came up in the lab we did this past week. What is ionization energy? It's the energy required to remove an electron from the atom in its gaseous state. So if we take sodium and put enough energy into it, we can get an electron to come out, and that forms a positive ion. The ionization energy goes in the opposite trend as the size. A smaller atom is harder to pull an electron off of than a larger atom. And here's my politically incorrect analogy for that. It's easier to kidnap the child from a large family than a small family. There's a reason I don't take my kids to the fair. I couldn't keep track of them. Now the older two are in college, they'd be okay, they could help me. But when they were younger, who takes 6 kids to the fair by yourself? That's dumb. Somebody could take one so easily, right? Mom with one child going to the fair, you can keep your eyes on that kid. You can hold on to their hand. So larger atom, easier to take the electron. Smaller atom, more difficult to take the electron. I don't know why my pointer's stuck up there. Okay, what about a more scientific explanation? Because that wasn't very scientific. If we take an electron away from a group 1A element, that gives us a noble gas configuration. Is that a good thing? Yeah. They're all trying to get the noble gas configuration because that's a lower energy state. It's more stable. If we take an electron away from a group 7A element, that does not give it a noble gas configuration. That makes things worse for that atom. So let's look at the periodic table now. Not yet. Ionization energy decreases going down and increasing going across. They are inversely related. There's the periodic table. So the ionization energy decreases as we go down. The atomic size got larger. Larger atoms are easier to take electrons off of. As we go across, atomic size gets smaller, ionization energy increases. Okay, so it's opposite. So we should be able to answer questions like this. Which one has the higher ionization energy, magnesium or strontium? I'll have to find them in the periodic table. There's magnesium, there's strontium. Higher ionization energy. Does that mean a bigger atom or a smaller atom? Smaller. The smaller atom will have the larger ionization energy. It's harder to take the child from the small family. I don't see anyone in line trying to take my children, by the way. There are days when I would have paid someone. But I didn't. So magnesium is going to be smaller than strontium, right? So which one has the higher ionization energy? Magnesium. The magnesium. So that's the answer for that one. How about the next one? And you can answer questions like this even though you don't know which element that is. All you have to do is find it on the periodic table. It's right over here. That actually happens to be indium, and Te is tellurium. So here we have indium and tellurium. Which one has a higher ionization energy? Tellurium, the T one, right? The T one. We don't even have to pronounce them. As we go across, they get smaller. These halogens right here, they really want to gain an electron. They're going to be really unhappy about you taking an electron away from them. Because if fluorine gains one electron, it's got a noble gas electron configuration. And that's what they're trying to do when they bond and form compounds. How about carbon or phosphorus? Here's carbon, here's phosphorus. Going across, ionization energy is going to increase because the atoms are getting smaller. Going down, it decreases because the atoms are getting larger. Can't tell. If you had to choose, I'd say probably go with phosphorus, but it's really iffy, really iffy. So opposing trends, can't tell. I won't do that to you on a test. Could show up on a lab, though. Fluorine or sulfur? Well, let's get these guys out of the way here. Here's fluorine, and here's sulfur. Fluorine. Fluorine's going to win. Because here the trends are reinforcing. Going across, higher ionization energy. Going down, lower ionization energy. Okay, any questions? It's just the trends. The trick is to remember which direction.
Okay.
Yes?
So going down the periodic table, the ionization energy decreases?
Increases.
Increases.
One approach is to remember how the size changes, and then remember the large family, small family. It's opposite, high ionization energy for small radius. Missed a slide. Metallic character is another trend. How metallic or how metal-like is this particular element? Metals tend to lose electrons. Non-metals tend to gain electrons. What we see is that as we move across the periodic table, ionization energy is increasing. It's harder and harder to remove an electron. Things are becoming less metal-like. So metallic character is following the same trend as atomic size. This one, I think, is really the easiest one to figure out. Do you remember the significance of this stair-step line? This guy right here. What does that divide? The metals and the nonmetals, right? So here are our trend arrows, but let's look at this period, period 4. As we're going across metal, 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 semi-metal, semi-metal, nonmetal, are they becoming more or less metallic? Less metallic. These are actually nonmetals. So as we go across, metallic character decreases. Coming down, let's look at group 5. Non-metal, non-metal, semi-metal, semi-metal, metal. As we go down, metallic character is increasing. Metallic character and atomic size, same trend. Ionization energy, opposite. I don't know about you, but I'm getting tired of these. Let's just do A and B. So tin or tellurium? Here's tin, here's tellurium. Which is more metallic?
Tin.
The tin. Because it's over here in the metals, right? You just look at the periodic table and see that trend. This is the nonmetals and these are the metals. So tin is more metallic. How about silicon or tin? Here's silicon and here's tin. Which one's more metallic? The tin. That make sense? Okay, so that should help you out answering the questions on that worksheet. Okay, there we go.